Good morning, everyone. I am Tirupati Jaydeep from the Department of Artificial Intelligence and Machine Learning. Today, I am presenting my mini project titled Decoding Digital Addiction via Device Gaps. This slide shows the agenda of my presentation. I will start with an introduction to the problem and explain the motivation behind the project. Then I will discuss the statement of the problem and the scope of the project. After that, I will explain the methodology, architecture and UML diagrams. Finally, I will present the results, conclusion, future work and the references. Problematic internet use, also called PIU, is a serious mental health concern among children and adolescents. It refers to excessive and uncontrolled use of internet. Problematic internet use negatively affects the sleep patterns, academic performance and social behavior. This issue has become more common due to increased smartphone and device usage. Hence, early and accurate detection of PIU is very important. Problematic internet use is highly correlated with disorders such as anxiety and autism spectrum disorder. Many affected children show poor attention and impulsive behavior and emotional instability. Currently, diagnosis depends on the questionnaire based assessments. However, these methods are subjective and prone to bias. The first major challenge of the is subjective in assessment. Parents may not be aware of secret or nighttime internet usage. Children may intentionally underreport their internet usage. This leads to incorrect PIU severe estimation. Wearable devices correct the actigraphy data continuously. However, traditional systems treat device as non-wear data loss. Such data is either removed or guessed using the imputation. This process ignores important behavioral information. This issue is referred as an actigraphy blind spot. Another major issue is sorry the project focus on the compliance phenotyping. This means analyzing how users wear or remove devices instead of activity levels. Non-wear behavior is studied. A hybrid deep learning approach is used. This approach improves the objectivity in the PIU prediction. The target audience includes the pediatric clinicians and the mental health researchers. School-based screening programs can also benefit from the system. This project delivers a trained compliance net model. It also identifies the behavioral phenotypes among the users. Performance metrics and documentations are provided. This project uses the Healthy Brain Network dataset. It includes the actigraphy, brain telemetry, and ambient light data. Novel compliance metrics are extracted from the raw data. Deep learning models are trained using this dataset. Unsupervised clustering is applied to discover the behavioral patterns. Coming to methodology, methodology follows a structured pipeline. It begins with the data collection from the HBN dataset. Next, data pre-processing is performed. The model deployment, development and system integration follows next. Finally, the testing and the evaluation are conducted. Raw actigraphy data is first cleaned and aligned. Compliance vectors are extracted from missing data patterns. Soft DTW clustering identifies the behavioral phenotypes. Transformer based modeling predicts the PIU severity. Results are evaluated using the cross validation. Next, coming to the architecture, the raw data is given as input for the future extraction. This extracts the features are passed into the clustering modules. These clustering modules are passed to the transform model which processes temporal patterns. The final output is the problematic internet use severity prediction. Next is a use case diagram which represents the user interaction. Here the user uploads the actigraphy data to the system and processes the data automatically. PIU severity and behavioral phenotypes are generated here. Next, another use case diagram shows the administrator responsibilities, which includes the managing the datasets and the system settings. admins ensure that the data integrity and the performance. System monitoring is also handled by the admins. The class diagram shows the structure of the system. It includes the classes for data loading and pre-processing. Feature extraction and modeling classes are shown. Relationships between the system components are defined. This diagram represents the object-oriented design. The sequence diagram shows the complete data flow. It starts from the input by the user. Feature extraction is performed step by step. The model predicts the PAU severity. The result is returned to the user. This diagram focuses on the compliance vector extraction. Raw telemetry data is processed sequentially. Battery life non-wear patterns are analyzed. Behavioral features are generated. These features are passed to the model. The compliance vector extraction engine is used. It transforms missing data into behavioral signals. This follows the missingness as behavior paradigm. This approach is novel and effective. It improves the detection of the severe PAU cases. Soft DTW k-means clustering algorithm is applied. It groups the similar compliance behaviors together. Transformer based missingness encoder is also used here. The multi-head self-attention captures the long-term patterns. Ordinal prediction ensures the severity order consistency. Actigraph WGT3X BT sensors provide the raw data. They include the accelerometer, light and battery sensors. Python is used as a programming language here. PyTorch is used for the deep learning and the TSLearn is used for DTW based clustering. Now coming to the implementation, it is entirely implemented in Python. Feature extraction scripts the extract compliance matrix. This model is training using the HBN data. Transformer architecture is implemented using PyTorch. Outputs include the severity scores and the attention maps. Coming to the code segments, this shows the compliance vector extraction. It computes battery, neglect and non-wear metrics. Next, DTW clustering code groups behavioral patterns and the transformer code performs the severity prediction, and finally these components form the core logic. This slide shows the end-to-end pipeline. All modules are integrated together. The raw data is converted to severity scores. The pipeline ensures the modular and the scalable design. This improves the maintainability and performance. The system outputs the predicted PAU severity. Severity is represented using the severity impairment index within a range of 0 to 4. Behavioral phenotype is also displayed. Attention maps explain the model decisions. This improves the interpretability for the clinicians. This slide shows the sample output results. Different severity levels and the behavioral patterns are clearly distinguished. This helps in the early intervention. This output supports the objective screening. Multiple test cases are designed. Normal, moderate and severe behaviors are tested. Boundary cases are also included. System stability is verified. Accuracy across all the scenarios is ensured. Extreme non-wear patterns are also tested. Battery neglect scenarios are evaluated. Neglect time removal are also analyzed. The system handles all the cases robustly. This confirms the reliability. The system achieved an 88% accuracy with a FN score of 0.86 and a quadratic weighted kappa score of 0.51. These results outperform the traditional methods. Severe PAU prediction is significantly improved. Device non-wear behavior is a strong problematic internet use indicator. ComplianceNet effectively uses the missing data. The hybrid model improves the prediction accuracy. The system provides objective diagnosis. It supports the scalable mental health screening. The future work includes the integrating the clinical notes. The self-reports can be combined with the sensor data. Social behavior indicators can be added. This will further improve early detection. These are the few references that I have been helping to do my project. Thank you.